Let's consider a scenario in which we've got warm fluid flowing through the inside of a pipe and cool fluid flowing over the outside of the pipe. And heat's being transferred from the inside of the pipe to the outside. Some of the things that we know are the mass flow rate, the temperature at the inlet of the pipe, and the temperature at the outlet of the pipe. We also know the temperature of the fluid, T infinity, flowing over the exterior of the pipe, and its speed, U infinity. The pipe itself is built up of a number of layers. We've got an interconductive layer, we've got a contact resistance, and then an outer conductive layer. When we examine a cross-section of the pipe, we know some of the geometry. We know the inner diameter of the pipe, we know the outer diameter of the pipe, we know the radius, the inner radius, I'll call that R1, and we know the radius R2, and we know the radius R3, which is simply equal to the outer diameter divided by 2. And the inner radius, of course, is equal to the inner diameter divided by 2. We also know some material properties. The inner conductive layer is we have a thermal conductivity of K1, and the outer conductive layer is a thermal conductivity of K2. Between the two layers, we do have a thermal contact resistance, and note that this has dimensions of meters squared degrees centigrade per watt. Because the interior fluid is warmer than the exterior, we find that heat flows radially outward from the pipe, from the inside to the outside. And as it travels through, there's going to be a total of 5 thermal resistances. There'll be a conductive resistance on the inside, a convective resistance through the first layer, a contact resistance, and a convective resistance on the outer layer, and finally a convective resistance from the outside of the pipe into the surrounding fluid. So if we examine it from this perspective, we've got a mean temperature, I'll call that Tm, and it's a function of the position x. The 5 resistances, again, there's going to be a convective resistance to the inner wall. There'll be a conductive resistance through the inner wall. There'll be a contact resistance, which I am not able to show here, but then there's another conductive resistance, and finally a convective resistance into the other fluid with temperature of T infinity. If we draw out our resistance network like this, these 5 resistances are in series: convective, conductive, the contact resistance, another conductive, another convective, and the driving force is the temperature difference between the inside of the pipe and the exterior. The ultimate goal of this problem is to calculate the mean temperature as a function of x, where x equals 0 is the entrance of the pipe and x equals L is at the exit of the pipe. Well, one thing we definitely know is that the temperature is equal to the inlet temperature at x equals 0, and the big question is, what does that temperature profile look like as x goes to infinity? So figure out the mean temperature at any value of x. And we have to be careful here when we specify what this mean temperature actually represents. Now, if we looked at a cross-section of the fluid from this perspective, the fluid here at the center will be warmer than the fluid near the exterior. And it has to be warmer because the heat's flowing from the inside of the pipe to the outside. What we are not going to know is anything about the temperature gradient across the radius of the pipe. We're not going to be able to say anything about the temperature profile from R equals 0 to R equals R1. We're just going to compute an average temperature. And as in most cases, we're going to start with an energy balance in which we have energy entering minus energy leaving plus any rate of energy being generated, and that's going to be equal to the rate at which energy is being stored within our control volume. Well, in this case, the water itself is not generating thermal energy, and we're at steady state, so the rate of energy stored is equal to 0. So what we're left with is the energy entering our control volume minus the energy leaving is got to be equal to 0. And I should note that the control volume we're dealing with here is a slice of water, and the water has a length, we're going to say this control volume has a length of dx. So a very, very thin slice of the pipe. So if we look at the flow of energy, we've got energy being convected in from the backside, energy is being convected out from the front of our control volume, and energy is being conducted out radially away from our control volume. So we have one way for energy to get in and 2 different ways for energy to leave our control volume. Well, let's deal with the rate at which energy enters. It's going to be equal to the mass flow rate multiplied by the heat capacity times the mean temperature evaluated at x, and it's going to be leaving in the same manner. It's going to be convected outward, m dot Cp multiplied by the mean temperature evaluated at x plus dx. Another way for heat to leave is through this resistance network. And I'm going to draw it up like this. I'm going to say the driving force is equal to the mean temperature at some location x minus T infinity is the driving force. And what we're going to do is divide that by a resistance. I'm going to call this dR total. And this small amount of resistance is similar to the resistance you might consider for the entire pipe, except we're looking at a very narrow slice. And this is how we're going to represent that differential resistance. So we've got the convective resistance 1 over HA, we've got the conductive resistance in cylindrical coordinates, we've got the contact resistance, and here I'm dividing by the area to make sure that we're in units of degrees C per watt. We've got another conductive resistance, and finally the convective resistance on the exterior. What I'm going to do now is multiply both sides by dx over L. What we find is that the dx's will cancel out in our expression, and what we're going to be left with is something that we would traditionally know as the total resistance along the entire length of the pipe. So when we rearrange this differential resistance is going to be equal to the total resistance multiplied by L over dx. And we're going to make that substitution here. So examining this equation, the rate at which energy is entering minus the rate at which energy is leaving is equal to 0 because it's at steady state. Simplifying the third term, we're left with this expression, and then we'll divide the equation by dx. When we take the limit as dx goes to 0, we're left with negative m dot Cp times the mean temperature dTm dx. So this is what we're left with, and then we'll proceed to isolate the differential so that we can proceed with the integration. So with the differential isolated, we'll proceed to separate and integrate. We'll move the dx to the right-hand side of the expression. We'll be left with dTm over Tm minus T infinity. We're going to integrate that from the inlet temperature to the value of the mean temperature at some value of x. So we're going to integrate x from 0 to some value of x. Well, evaluating the right-hand side is easy enough. We're left with x over R total L. So the left-hand side evaluates to the natural log of the mean temperature at some value of x minus T infinity divided by the inlet temperature minus T infinity. And that will be equal to what we had before. So after exponentiating both sides and doing a little bit of algebra, we're left with an expression for the mean temperature as a function of x. When we look at it, if x is equal to 0, e to the 0 is equal to 1, and we're left with the temperature. The mean temperature is equal to the inlet temperature. At the other extreme, if x goes to infinity, the right-hand term goes to 0, and we're left with the mean temperature, which decays to T infinity over a large value of x. A graph of this function, then, the mean temperature decays exponentially, asymptotically, approaching T infinity over a large value of x.